Now finally we have the cartoon guide to physics. Part 2. Electricity and magnetism. I'm not going to show any of the photos though. That's going to be great. Now I'm going to have to do all this from memory. Charge. Let's start with charges. Charges are an awesome part of physics. Oh, if only I could find it. Found it. Now, charges are basically what things seems to work out with. It's the reasons why charges go ahead in positive, negative, and those are probably the other ones. The only other charge is neutral, and that's very boring, so we're not going to ignore that. And this is basically used in electricity. Also, we mainly use electrons with the negative charges to do all this. And with that, you're basically creating yourself the greatest physicist, the greatest experiment of all time to create electricity. And that is just the darn tooting thing I can think of. Next thing we're going to have to talk about is basically how the nucleus can be used to split into it. In fact, alpha radiation, beta radiation, gamma radiation is just the nucleus spitting out helium nucleus, which is the alpha particle, separate neutron or an electron, which is the beta radiation, and gamma radiation is just light rays it's emitting. It's just a ray. It's a wave it's emitting. It's a light wave it's emitting, which is very, very dangerous, and I highly recommend not using. And of course, that's also why static electricity seems to work out. And it's because of static electricity that balloons stick in your hair, and silk can electricize or magnetize a piece of glass rod. Next, we have the electric field. The electric field is an interesting subject in itself. In fact, it's just about electrons having fields around it. It's more like the magnetic field, except it starts off at protons or positive particles. The electric field lines start off from the positive particles, like this, and if you draw it like this, and then they end at negative particles. So it's more like a field of electricity that can be used, that we can harness it just so we can use it. And then we have capacitors. Capacitors are just what we use to harness the power of electricity, like switches or ways to transfer information. We use capacitors to basically create bytes, and it's also how batteries work. And batteries basically charge up in a short amount of time and then release all of it in a way shorter amount of time. We have electric currents next, and electric currents themselves are an interesting bunch. They're basically just the reasons why things seems to work out and why lemon juice is a really, really good electrical conductor. It's just what powers up that phone you're watching. It powers up these buds, galaxy buds. It's also the reason why chargers, like phone chargers, like this one that I doodled on, works. It's also the reason why this Apple, everything that's electrical, that's technological. Well, in the sense of electricity and computer stuff, is using electrical currents. In fact, there are different ways you can actually use electrical currents. You can turn on them with a light bulb and a switch. And if you want an analogy, you can think of like fish going around in a tank and going on and on and on until like a way is blocked. And I guess in the fish metaphor, there's a little error there because there's one way that the fish can still move. It's just that not in the circuit anymore. And I'm not going to even talk about ohms. So they are pretty important. Ohms are just the units that we use to talk about resistivity. Like good conductors are the ones like metals, like metal, silver, gold, copper, aluminum. While the bad conductors are just like paper or cloth or plastic, like all of those. And this filament in light bulbs are most likely created by tungsten because they are really, really, really good at conducting electricity and not breaking. And there are also superconductors. Superconductors are usually the ones that are cold. They cannot get a cold because they are already cold. In fact, that happens, and they're the ones that actually do the heavy lifting. In fact, with these new technology, we could eventually find maglev trains, which technically exist, but aren't that efficient yet. When was this published? Oh, it was published in 1991. Welp. So sad that laptops don't exist yet and when he wrote this book, which is a shame, which is a really, really big shame to be honest. And then that goes ahead, and then we can even use a galvanometer or like an anemometer to actually just check the charge. And yes, it is safe. Skip. Oh yeah, here's the next chapter. In the next chapter, we're going to talk about series and parallels. Now, series and parallels are just ways you can put a circuit together. Series are basically like this, the general way, the fastest way to do it, but it's the least efficient way because each of them get the same amount of volt, and the volt from the battery sent out must be the same by adding all these together. So each of them get 1/3 of the volt that the battery sends, which makes them, well, not as bright. What about if you put them in a parallel way? What if you put it like this? Well, all of them get the same amount of volt from the battery, and they don't have to share it at all. Meaning that, well, they still have to share the volt, like it still goes in a current, but it goes in like mini currents. Like the battery sends one current here, and sends another current here, and sends another current here, and does that all at the same time, which makes the bulbs light up. And it's also the reason why these little appliances, like light bulb and that light right over there, works. Also, I didn't turn that one on yet. Then we have magnetic fields, my favorite. Magnetic fields is just what makes magnets stick together or repel each other. In fact, they each are known to have a north pole and south pole. Also, there's like the in-between is it themselves have north pole and south pole. Each of them in each of the atoms inside have north pole and south pole. If you cut it in half, it turns into two magnets with each of them having their own north pole and south pole, which is kind of confusing. And if you put a lot of compass needles that are still magnetized, unlike on a sheet of paper, and then you put a little bar magnet underneath it, in a way, the magnetic field lines will start showing. And then you can use those magnetic fields to create electricity, and electricity to create magnetic fields, and and you can use that. And everyone was like, back then, were like, magnets, electricity, useless! They're not even connected together. Then the guy named Faraday is all like, you can create it. And so that happens, and they're all like, what a very intriguing study, but not very useful. And then they found out it was useful. Wow, you are a genius, man! And then we even find out things about magnetic fields and everything else that seems to exist about them. We even have to talk about permanent magnets, apparently, because they're permanent. They aren't, every magnet isn't technically permanent, but they will stay longer than temporary ones. Like, permanent magnets stay themselves, and you can't turn them on or off. Temporary magnets, the ones created out of electricity, they can be turned on and off, and you can make it stronger by just coiling a wire around a piece of unmagnetized metal, just stronger and stronger, and then you basically create electricity to create a magnet. And usually iron nails work out well, so they're the best. And then we have AC and DC. AC and DC, AC and DC. And remember, this is the 1990s. Imagine it like that. And the AC and DC, AC and DC. No, that's not the song I'm talking about. I'm talking about the current, which is the thing the song's based on. Here's how it works. AC current is the one that everyone's using nowadays in their homes, because DC turns out is weak. You remember, like, think of it like this. DC is basically the series circuit, and AC is the parallel circuit. And DC is safer to create, sure, but AC is more energetic, and it's cheaper to create too. And you don't have to live next to very, very big power stations to do that either. And nowadays you went nuclear, so it makes it more dangerous to live near power stations. And finally, and who do you think won this current war? Of course, AC, but who was the competitors? A guy named Westinghouse and a guy named Edison. Thomas Alva Edison, the guy who invented the light bulb. He's all like, DC's better because it's safer. And then Westinghouse is like, Nikola Tesla's invention is better because, first of all, it's safer. Not safer, but it's more efficient and it's cheaper to create, and people don't need to live near dangerous powerhouses. And Edison, of course, lost the battle. Yeah, because he made a very, 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 very bad bet. Yeah, it's also the reason why people don't tell you not to put your fingers in the electrical socket. And that's all I have to say now. And now, finally, this is all I have to say. So, that's all the cartoon guided physics. The first part was very, 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 very boring, I knew, because there wasn't much to actually talk about motions, and yeah. But now that we're talking about electricity and magnetism, that is the more fun part. And that's it. Hope you guys enjoyed this episode. See you guys soon. Shout out. Peace. AC/DC, 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 AC/DC.